To our public night tonight. Our speaker tonight is Professor Lawrence Rudnick of the University of Minnesota. And he is an old friend and longtime colleague of mine. So Professor Rudnick went to college at Cornell University, and after that attended graduate school at Princeton University, receiving his PhD in 1974. Following Princeton, he went to the National Radio Astronomy Observatory in Charlottesville, Virginia. Actually, the offices were in Charlottesville, Virginia. The radio telescopes were all in Greenbank, West Virginia. And that's where I met Professor Rudnick in 1976 when I came in as a greenhorn postdoc. And Professor Rudnick really contributed to the fantastic scientific atmosphere that I experienced there. And NRA was just a wonderful place to be. And a good part of that was due to Professor Rudnick and a number of other of our colleagues. His areas of research characterized as really in the study of extragalactic radio sources. These would be radio galaxies and quasars, and particularly radio sources and clusters of galaxies, not only the galaxies themselves, but what's called the intra-cluster medium, which is kind of an atmosphere in which all of the galaxies move around. And he's made a number of very important contributions to that for many years. One of the great things about Professor Rudnick is that he has a long perspective on radio astronomy, which is part of his talk tonight, and has seen a tremendous evolution in the subject during that time. So his talk tonight is entitled Odd Radio Circles and Even Odder Radio Cubes, and we're really delighted. So Larry, thanks for giving us this talk, and I'm looking forward to hearing your presentation.
Great. Well, thank you guys for having me. I've never heard such a good euphemism for being old as saying that I had a long perspective on things. But let me, in fact, take you back a little bit. In fact, there we are 50 years ago when I was a graduate student at Princeton. And that's my ID card. And I don't know whether people recognize the guy at the bottom. You can just yell out if you want to unmute yourself, if you know who that is. He was my thesis advisor.
I just also want to add for everybody, if you have questions, you can go ahead and unmute yourself, and ask those questions, or you can put it in the chat and we'll ask them.
At any rate, so this is Dave Wilkinson, who the WMAP satellite was named for. So this is the WMAP satellite, and that was, and this is the image. Are you guys seeing my arrow?
Yes, we do. Yeah, we can.
Yes, we do, Larry.
Good. Okay, so that's fine. So I wanted to take you back to my graduate student days because I wanted to ask the question, am I a real astronomer? So when I talked to the Minnesota Astronomical Society, which I have for many years, I sort of have to embarrassedly admit I don't really know my way around the sky, so I'm not sure I'm a real astronomer. I mean, I do research in this stuff, but there's so many things that you guys know that I don't know. So when I was a grad student, one of the things that Dave had me do was to set up an experiment on the roof of the building in Princeton and try to look for things that we didn't discover, but were in fact discovered later on, called fast radio bursts. And so I built an antenna, stuck it on the roof, had a receiver system, and there were just lots of noise, just constant stuff coming in over the receiver. And so I stuck the output of the receiver onto a speaker just to see what these signals were. And a number of the things were amateur radio, ham radio operators. And I took the loudest booming one and looked him up. This is, of course, before the internet. So looked him up somehow. I don't even remember how. There must have been some handbook where you could look up the call signs and figure out who the people were. And he was just about 10 miles down the road from Princeton, and he was doing moon bounce. And I don't know if there's anybody here that's doing moon bounce, but it was just really cool. And he said, come out and see my rig, see my setup, and maybe we can try to look for some radio sources. So he had an antenna that looked like this, And this isn't him, but this is just what his looked like. And it's kind of a mesh surface, and he got it as a spinoff from Bell Labs, which was kind of local there in New Jersey. And he had a sighting scope that he would just use to sight on the moon and then talk to amateurs all over the world. So he said, well, you know, bring some information and we'll go look at radio sources in the sky. So I brought my copy of Krauss, which was kind of the Bible in radio astronomy. And in the back of Krauss, there was a couple of pages of tables of strong radio sources and their RAs and DECs. And so I figured, well, we're going to point. So I just turned to the back there and pointed out, you know, one of the sources. And I said, why don't we try to look at this one? And he said, well, it's not up now. And I kind of had no concept of LST or what to do or how to point a telescope. And I was just completely lost. And he said, but you observe at these national observatories. So how do you do it if you don't know your way around the sky and you don't even know how to calculate RA minus LST to figure out hour angle and where to point the telescope? I said, well, this is the way you point the telescope. You hand the operator one of these things. And these things, the telescope operator knows, well, you just sort of type them in. I mean, it reads the coordinates off the card and the telescope goes and points itself. So this is just to tell you that I'm not a real astronomer. I do research in astrophysics, but I don't know how to point things in the sky. And still I've managed to do some things, and hopefully I'll entertain you a bit with some of the stuff that I've been working on. So the radio astronomy community worldwide now is geared up and building the square kilometer array. The square kilometer refers to the amount of collecting area. So it's a telescope which has got the collecting area of a square kilometer. If it were a filled array, it would be a kilometer, you know, on each side. But that's not the way you build these things. You don't get the resolution that you need. And it's completely impractical to build 1 square kilometer of collecting area and focus it. And you build basically interferometers. You build hundreds and hundreds of small telescopes which work in concert, and that's what we're in the process of building. There were so many different technologies that had to be developed for the square kilometer array that there have been a variety of telescopes over the years, including the ones that we used in Green Bank as part of NRAO. They had interferometers there. That was a great learning process. And then the Very Large Array in New Mexico was another major step. There were telescope interferometers all over the world. Now, this next generation on the road to the square kilometer array, there are 2 major precursor telescopes, precursor arrays, one in South Africa and one in Western Australia. And these 2 telescope arrays are in the process of doing major surveys now, lots of pointed observations as well as major surveys of the sky, and learning what the sky looks like at these new levels of sensitivity and resolution, learning how to deal with the very wide fields of view that we are looking at, and just developing the technologies, both the hardware and the software that are enabling the square kilometer array. So what I'm going to show you tonight are results from these 2 precursor arrays, the one in Australia, which is called ASCAP, and the Southern Africa, the South Africa telescope, which is called Meerkat. And just to give you sort of a little bit of a graphical hint of how these things are developing, these are the dates that various surveys have been were published. And this is the log of the number of sources that are in those surveys. And so you can see there's been an enormous growth over time. I mean, this is a long time. This is 1940 from Reber's first telescope, where he basically saw one object, which is the Milky Way. And now we're in the range of 10 to the 8th sources in the sky. So tens of millions of sources are being detected in LOFAR in the Netherlands. EMU is the ASCAP survey, and this is another sky survey going on at the VLA. And Meerkat, the mighty survey, is down a bit lower. It is focused on smaller areas of the sky and going deeper, but the growth has just been enormous, and there's enormous challenges just from looking at these numbers of telescopes. So the single dish interferometer telescopes at the higher frequencies now are doing instead of a single receiver at the focus, they have what are called phased array feeds, which can feed to a large number of receivers, and you can simultaneously observe very wide areas of the sky, and that gives you a lot of speed for when you're doing survey work. And then this is what telescopes look like at very low frequencies. And I mean, they're just various crazy shapes at the very lowest frequencies. Dipole would be the simplest way, and you just get large numbers of arrays. This is what the LOFAR telescopes look like, and this is what the Murchison Wide Field Array in Australia looks like now. This is just to give you a kind of a visual impact of what these telescopes look like. So the question is, what are we trying to do with this new generation? There's extreme sensitivity, very large numbers of sources, and there's a variety of different sort of very broad goals. And some of them, and so this is just sort of a snapshot to show you where things are headed, over the next 10 to 20 years. Studying galaxy evolution, to very large redshifts, probing the dark ages, the very first black holes to be formed, searching for life through things like absorption experiments, through atmospheres of exoplanets and newly forming star systems. Cosmic magnetism, that's one of the things that both Steve and I have been interested in for a number of years, is the strong magnetic fields that are present in some of these sources. And then people are doing some very clever things about using pulsars to do sophisticated timing experiments and really test some of the ideas of general relativity. However, with all of these goals in mind, one of the things that people are very much aware of is that whenever you open up some new areas of parameter space, your most interesting discoveries are going to be the ones that you didn't expect. You don't know, what it is that you're doing. We don't know what it is that you're going to find. You may know what you're doing. You don't know what it is that you're going to find. And so the question is, well, what do you do about that? If you know that the things that you are going to be the most exciting are the things that you don't know about, how do you prepare yourself for it? And partly you need to prepare yourself intellectually to just be open to new things that are coming up. And partly you need to have a flexible design so that either the software or even the hardware can be somewhat reconfigurable. The software, give you tools that you can say, well, yeah, that was our standard analysis, but we're going to have to look at things a new way because we're discovering something. So Ray Norris, who was one of the driving forces on the Australia telescope, in fact, put together lists, and I'm not sure whether this is his list or somebody else's, but this is a great, interesting list of major discoveries in astronomy that were that were unexpected. They were things that were discovered, but nobody was out there looking for them. So radio galaxies, for example, which I'm going to show you some of tonight, that was unexpected. We had no idea what was going to happen when you looked at the radio sky. The cosmic microwave background, as most of you know the story, was a complete accident. The expansion of the universe was a discovery. It wasn't that somebody had predicted that the universe was going to be expanding and then the observations were done. Pulsars, gamma ray bursts, dark matter and dark energy. And so it is kind of remarkable that the things that you would recognize now as major discoveries in astronomy were not the classic, what we sometimes teach inappropriately in schools, that what science is to have a hypothesis and test it. That's part of science, but especially for those of us in astronomy, the way the science is done is you build new tools and you go out and you look and you see what you can find, and you be open to interesting things that you find. And I'm going to pass over that slide, but the same thing happened with the Hubble Space Telescope. When you look at the really major discoveries, they were not the ones that were part of the key science projects defined prior to the launch of the telescope. Okay, so what we're looking at here is we're gonna look at some results from what was called the pilot survey for this is the Australia telescope, the Australian SKA Pathfinder. So a couple of years ago, we did a pilot survey of limited area of the sky to sort of test to make sure all the survey parameters were going to work. And this is an image. This is a typical image of what the radio sky looks like over a wide field. So one of the dramatic things about this survey is that you can get a 30 square degrees, so 5.5 by 5.5 square degree patch of the sky all at once. So you track the sky for 10, 12 hours, and then you make a map of this very large fraction of the sky. And that's what allows you to do, that's what allows you to survey the whole sky in a couple of years. The way we were doing radio astronomy was to look at really tiny patches. And if you wanted to survey the sky, you could very quickly scan the whole sky, but then you couldn't go very deep and you couldn't see very many things. So now we can both cover very wide areas as well as go sensitive enough so that you can detect lots of objects. So I'm going to, if you look at this cyan rectangle here, we're going to zoom a little bit in on it so you can see the amount of detail that's in here. And so you can see that we're just filled with all of these very, very faint sources, as well as there's a couple of nice big radio galaxies here. So this is a really big one. There's another one here. There's another big radio galaxy there. There's a few little doubles and triples and things like that. A lot of them are still just compact sources, but you can see a number of the extended radio galaxies there. And there's just lots and lots of these very faint objects as well. And if we zoom in further, you can, see how many of these things there are. In fact, we are reaching what radio astronomers call the confusion limit. We're not quite there, but we're very close to it. And that is that if you go a little bit deeper, the sky gets so filled with sources that everywhere you look, there's a source there. You're just looking deep enough. And we have been in that regime. This isn't the observation that does it, but we have been in the regime where the entire sky is actually lit. And then you have other problems figuring out what's a source and what's just a combination of things that are blended with each other. So I think that's the end of my Zoom. Okay, so Ray Norris, who was one of the drivers of the from the ASCAP telescope, the survey that we were doing was called EMU. The Australians name all of their surveys after animals. And so EMU was the name of the survey that I'm going to be showing you stuff from. And it stands for Evolutionary Map of the Universe. First you find the animal, then you figure out the words that kind of make sense to go along with that. And he wanted there to be a group that was focused on what he called WTF, which I will not translate for you because we're in polite company, but if you don't know what it is, you can ask one of your colleagues. And the journals would not let him use that. They would not let him say that one of the goals was WTF. And so he just had to say, let's focus on the unexpected things and see what we can find. And what he found was that there was a group of objects which didn't fit any of the things that we knew. And this is kind of an unexpected, but expected, in the sense that when you start looking at millions of objects, and we're not quite up to that yet, but when you start looking at very large numbers of objects, then the things that are very rare are going to start showing up. And if you're ready to recognize them and look for them and recognize them, then that's what opens up the discovery space. So what he found were a group of circular objects, and he called them odd radio circles. So are circles really odd in radio astronomy? And the answer is no, because we have lots of circular things. We have supernova remnants, for example. We have a number of planetary nebulae, even some H2 regions, might look kind of circular and stuff. So there were things that we knew about that were circular, but we could very quickly rule out that these were not those. We were not looking at spiral galaxies face on. We were not looking at supernova remnants. We're not looking at planetary nebula. Some of these things had galaxies right in the center, an optical or an infrared galaxy right in the center. And you can see one here. This is the radio center, but there's an optical galaxy there. So these were circles, some of them around central galaxies and some of them not. So it wasn't clear how many, different ones we had. And the question is, what were those? What were they? So I think one of the first things you do when you kind of find rare objects is you need to try to convince yourself it's not some kind of strange instrumental effect, some kind of distortion to the interferometer that happens kind of every once in a while, but when you're looking at very rare things, they would pop up. So so it was important to go to other telescopes. So went to the Australia Compact Array, the Giant Meter Wave Radio Telescope in India, Meerkat, the telescope in South Africa, and asked people to look at these things with those, and sure enough, these things were real. So the question is, what are they? They're not normal radio galaxies. So if we go back, to this guy, this is what a radio galaxy looks like. The optical host would be somewhere in here. You have a jet going north, a jet going south. Often there's some bending as you interact with the intercluster medium or the intergroup medium. And so sometimes you get these bends. Things get fluffy. Sort of as you get to the end, they get more diffuse. This is what radio galaxies look like. Here's a much smaller radio galaxy, a little tiny jet in here and a couple of bright spots. So that's what radio galaxies look like. They don't look like circles. And so the question is, what is forming these circles? They're roughly an arc minute across, so you can picture in an area of the sky. They were well resolved, and on the order of maybe 100 kiloparsecs or so, so much bigger than our own Milky Way. So these weren't tiny little things inside galaxies. They were big circular or spherical objects that were way outside the optical galaxy. So Noah, why don't I take a break for a second here, since I've just been talking rapid fire, and see if people want to ask me questions and stuff, and then we'll move on.
Absolutely. I'm gonna invite everybody. If you have a question, go ahead and unmute and ask it, or I can read it off of the chat if you want to put it in there.
Nobody else seemed to be asking questions, but being a ham operator, what are the frequencies that you're dealing with?
Oh, very good. Yeah, I should have said it. Most of this kind of radio astronomy is done at centimeter wavelengths, which means you're at around 1 gigahertz to 10 gigahertz or so. So the observations, all of these radio telescopes, they go down to about 60 megahertz or so is the lowest. And then, of course, below that, you start getting messed up by the ionosphere. So 60 megahertz would be about the lowest. The highest, it just keeps going up into what we would call the millimeter range, but typically most of this work goes up to maybe 15 gigahertz or so. And then, of course, there are other things that get into the millimeter range where people do other kinds of things. So typically 1 to 2 gigahertz is kind of the classic middle of that range where we're working. Good question.
Other questions? Maybe we keep going then.
Okay, yeah, we'll just keep going. So the question I'm posing is what are these radio circles? And while we're still trying to figure it out, and we don't know yet, although we have gone away, people start finding more of them. And the question is kind of, well, why didn't we see them before? Well, one was we didn't have enough objects in the sky, but the other one, sad to say, is we didn't know what to look for. We didn't know. We would look at a picture like this, for example, a radio picture, and just assume that we were looking at something like a face-on spiral galaxy and looking at the star formation in it, the spiral arms and stuff like that, and not bother to even look at the optical or infrared images you're trying to, decide what are you going to spend your time on. So part of it was we weren't looking at enough objects. We didn't have deep enough surveys. And part of it was we just didn't know what to pay attention to. And so now there's lots of these things. And some of them have these central objects in them, galaxies in the center, and some of them like this don't. And so this zoo of the kinds of things that we're looking at is just expanding. And so it's not clear that we're going to have one answer to the question. And so we've started, we're having this horrible, I don't know if it's horrible. Astronomers are horrible at naming things. We use type 1 and type 2 all the time, and those are meaningless labels. They don't convey any information. And the question is, how are we going to start distinguishing between these types that we're going to see and that we don't have an agreed upon terminology yet. But what we can say is some fraction of these odd radio circles have galaxies in the center. And so if we look at them, we can start asking, do they have a common set of properties? So one thing we find is they're not really pure circles when you make nice deep images. And so here you can see this is an image from Meerkat in South Africa, and there's more than one ring here. So it's not exactly clear what's going on. There's substructure, there's other structures that are inside here, but they each have a central galaxy, about 300 kiloparsecs, or a million light years across, in diameter, and they are quite rare. There's only about one of them every 50 to 100 square degrees. So when you think about that 30 square degree area that I showed you, maybe you would find one of these in there and maybe you wouldn't, and you could see how many objects there were in there. So they are, reasonably rare. And then if we look at the central galaxies, these turned out to be things at reasonably high redshifts. So a redshift of 0.5, redshift of 0.4 or so. And they're typically elliptical galaxies, although we have some exceptions to that now as well. People started looking at the environment and say, okay, well, are they in kind of a special environment? And we started looking for groups, because we already knew that if you look in clusters of galaxies, you do see special kinds of sources that you don't see elsewhere. And the question is, do these orcs sort of fall in special areas? And the answer is some do and some don't. It's just not there's not a clear answer to that. Most radio galaxies are in kind of higher density areas, so it's not a surprise to find the groups around them, but they're not preferentially in groups or clusters of galaxies. And this is just another way to look at the same thing, but in redshift space. So now we're looking at a closer look at the first ORC that was actually discovered, ORC 1. And this is what we were looking at before. And this is now a beautiful meerkat image. And I have learned how to make pretty images like that. I know among the amateur astronomers, some of you are quite expert in not only taking images of the sky, but also doing the kind of manipulations to turn them into these beautiful things. So Jan English, who's at the University of Manitoba, has taught me how to use GIMP. That it's not all that complicated and make these kind of ethereal looking images. So this is ORC 1, and it's got these multiple rings about it, around it. We have started trying to look at the other properties. Again, we don't know what these things are, but so the best thing you can do is just keep cataloging more and more information about them. So this is a picture, for example, of the fractional polarization. So each of these images, which I didn't say before, and I was just assuming, but I should have said, these are all synchrotron sources. Everything that you're looking at is a synchrotron source. So it's due to relativistic electrons that are spiraling around magnetic fields. So these are not thermal emission. They are synchrotron emission, non-thermal emission, very high energy electrons, relativistic, in the presence of a magnetic field. So when the magnetic field is chaotic, you don't get any polarization. When the magnetic field is ordered, you can get higher polarization. And so this is a map of what we call the fractional polarization, how ordered basically is the field. And on the outer edge of this, the periphery of this ORC 1, the fractional polarizations were quite high. And then this is a picture of the magnetic field structure that is around the circle. And you can see that it kind of traces the circumference of the circle. And this was kind of one of our major clues to support the idea that some kind of explosion or outflow is going on. Because if you had something in the center that was going to blow out, then it's going to compress everything. If there's something like a shock wave going out, it's going to compress things. And even if the magnetic fields in there are chaotic, they will tend to be lined up. They will be aligned by the shock wave and give you a structure that looks like this. And we knew that already from things like supernova remnants, much, much smaller things that are just a few light years across in our own galaxy, maybe up to 10 or so light years across. And now we're talking about, 300,000 light years across. So if this was an explosion, it was an enormous one, something that would have taken millions of supernova remnants, for example, to do. But it looks like that's what happened. Something blew out from the center and compressed the material around the outside. So that's one of the sort of standard models, basically, of it is kind of an explosion at the center. And I'll qualify that or modify that in a little bit based on something that just came out. So the idea is you have some kind of explosion at the center where we're not surprised you can get a lot of energy out, because if there's a supermassive black hole in the center, which is what we assume is there to get the normal radio galaxies, but instead of shooting out jets, the normal radio galaxies do, that perhaps for some reason there was an explosion at the center, and that blew out a shock wave, compressed the stuff on the outside, gave you those nice aligned magnetic fields. So that's one of the models. It's still there. There's another one that I was involved with, and we stuck out there for consideration the possibility that that there were actually two supermassive black holes here to form a kind of quadrilateral structure that was on top of the explosion. But whether or not that's true, and who knows, what I wanted to point out was an interesting part of the discovery of this object is that the discovery was made by machine learning. There are so many galaxies to look at and so many different things to see. The question is, how are you going to sort it out? And I'm involved, have been involved, and I'm still involved in various citizen science projects. And if you guys are interested in, if you've done any Zooniverse projects, we're about to start off a new radio galaxy zoo to get tens of thousands of people to look at images and find unusual ones. But in the meantime, Michelle Lochner in South Africa developed a machine learning algorithm, which just you trained on lots and lots of images, and it is basically an anomaly detector. It basically goes out and says what things don't belong with the others, what looks most anomalous. And on a project that we did on the Meerkat telescope, I was collecting interesting radio galaxies, and I had people give me maybe 100, maybe a couple hundred suggestions of things they thought were interesting. And then I combed through those, and I found 10 of them that I thought were really interesting, that kind of pressed the kind of scientific issues. And Michelle, in parallel, went and found 5 of them, the same ones, with her machine. And it's like, oh my God, it's a good thing that I'm retired now, because the machines are going to take over. So this was one of the ones that her machine algorithm found. She calls it astronomaly, to look for anomalies. And that's definitely going to be useful in finding some of these objects that we want to follow up on. So the other alternative, which just a week ago has become more attractive, is that instead of an explosion, that you have a burst of star formation. And it's not all that different from an explosion, except that it's not caused by a supermassive black hole in the center. It's the entire galaxy lighting up at once by having just a burst where lots and lots of stars form. And so the model was suggested that about 1 billion years ago, there's a burst of star formation in the galaxy, and the combination of all of the supernovae from all of the stars that are forming basically creates a hot wind that blows out and does the same thing that an explosion would do, sweeps up material, creates ordered magnetic fields around the periphery. And as of 2 weeks ago, it was not looking all that promising. There were problems with, can you get stars to sort of coordinate themselves well enough to have them all undergo this burst of star formation in a confined enough time? If you spread it out too much, you don't get a nice strong wind like that. It just sort of slowly diffuses. And recently, there was an article published, and they used this ORC-1 as an example, where they found enormous amount of emission line material on the scale of the galaxy, which they interpreted as evidence that there was this enormous burst of star formation that heated and ionized all the gas in there. So it looks like that may be a much more viable option than it was. So one way or another, you have this giant outflow of material from the star, reaching out again hundreds of thousands of light years to create these shells that we're seeing. And why that would happen just isn't clear yet. And then there's another class, and I want to go back because those are the orcs with central galaxies. But if you look at this one, for example, there is no galaxy in the center of this circle. There's a galaxy here, and there's another very faint kind of object. It's kind of circular object sitting there. So this must be a different kind of beast. And the question is, are there other ways to make these odd radio circles? And this is Chris Nolting, who is a postdoc now and does theoretical modeling. And the question is, suppose that you have a normal radio galaxy. So here's the optical galaxy, here's jets coming from the radio galaxy, here's another optical galaxy and jets coming from it, and then forming these lobes. Suppose that you form these lobes and then you hit them with a shock. So a shock comes by from somewhere else. Maybe you're in a cluster where there's been some mergers going on, maybe galaxies are merging, and you hit them with a shock and you form circles in these radio galaxies. So it has nothing to do with starburst winds or explosions. This is a normal radio galaxy, these kind of fat lobes here, but now you go hit them with something and you get the circular shock wave. And there's this beautiful example of one here. It was not called an ORC because it didn't stand alone. It was part of this radio galaxy structure. But sure enough, there are circles. And then Chris Nolting, this postdoc that I was talking about, thought of another way to do it. And that is that you could get precessing jets. And we see evidence of precession all the time from these radio galaxies. And those precessing jets, if you kind of look at them from the end on, would form circular type structures. And you have to sort of generously squint your eyes and stuff to see the circle there. But he was pretty convinced that that would be another way yet to make these things. So there is probably more than one way. Klaus Stolog in Germany and his colleagues are looking at explosions due to galaxies that are accreting material. As material falls into a galaxy, it sets off shock waves, and he wants to be able to make circular type structures with those shock waves. And so just an excuse to show you a pretty cosmological simulation. And you just want to notice kind of the explosive things that will go on as material collides and forms these various types of shock waves. And we do see that kind of stuff in clusters of galaxies as well. So there are lots of shocks that are floating around, and that possibly could be another thing as well. And then there's some that just turn out to be supernova remnants. So this was one that we weren't sure what it was. It was near the Large Magellanic Cloud, but now we've seen it in the infrared and the X-ray, and it is just a supernova remnant. So these are things that we've known about before, and we just need to be able to sort out these beautiful circles that are not ORCs, they're supernova remnants, but sometimes they're not sitting right inside of a galaxy that we can recognize. And so we have to be able to sort them out. And this mystery thing, I'm just going to skip here because I'm running close on time. So here is just one of those double structures that I said was possibly an old radio galaxy, 2 lobes, and then a shock comes along and hits it. So this was one of those ORCs that we were looking at. The optical galaxy is here, 2 jets form 2 big lobes, and then something causes a circle to form in the lobes. And that's almost certainly happening in some of these situations. So we're going to have to sort out how many different kinds of ORCs are there. What are the kinds of models that are going to help explain what's going on? So we're going to find more of them. We're collecting, this is kind of cute. Ray set up something called the Even Messier catalog. And everybody that finds some can go ahead and stick them on the website so everybody can look at them. We're doing more simulations. We're going to do more spectroscopy of the host galaxies. And I just talked about that one that found evidence for starbursts. So that's the game. And we're also going to use, machine learning to help pick up more of these. So I'm about to switch topics completely. So I'm going to stop here and see if there's questions before we go on.
Any questions? You can go ahead and unmute. Okay. I think we can just keep going then.
Okay. So this is the second half of the talk, but since I've used up all my time, I'm just going to sort of briefly show this to you as just sort of a tease for the stuff that I'm working on now, that some new stuff that I'm working on. And I just want to point out that the one of the major challenges in astronomy overall is to sort out the 3D structure of objects from the two-dimensional images that we see in the sky. And I had a grad student a number of years ago that did this for supernova remnants, to sort out the 3D structure using the velocity. This was Tracy Delaney's work on Cassiopeia A, and she was able to sort out the 3D structure by looking at velocities. So it's one of our classical problems. How do we visualize things in 3D when we see a 2D picture? And so let me just introduce you quickly to Michael Faraday, who found that there was things that he called heavy glass, and that this heavy glass, which was doped basically with metals, would rotate the plane of polarization. If you took a polarized wave and put it through the glass, it would rotate. And the longer the glass, the more rotation there would be. And this was called Faraday rotation. And so Faraday rotation has been used for many years in radio astronomy. And what it does is it measures, there's no glass between us and the radio source, but it measures the amount of magnetic field and number of ionized electrons that are on your path. That's it. Magnetic field, number of electrons, and the more there is of that, the more rotation there is. Typically, when you look at a radio source, there may be material that's in front of it. So, for example, the Milky Way is in front of all of the extragalactic radio sources that we see, and different parts of it will go through different amounts of material, and they will rotate by different amounts. However, if you were lucky enough to get this situation where your radio galaxy, which I'll show you here, is sitting in the middle of a medium with magnetic field and free electrons, then this part is seen through more material, and this part is seen through less material, and perhaps you can use it to tell how far are you looking through the material, that it's actually a measure of physical depth. And so I have been working on techniques to help us visualize, are we in this situation where everything is just chaotic, that there'll be some amount of rotation of the angle from here, and a different amount here, and a different amount here, a different amount here, and there's no pattern to it because it's just completely unrelated stuff that's in the foreground? Or are we looking at this? And there's no mathematical techniques yet developed in order to distinguish between these two, but that's what we need. And so I've been doing some very subjective type stuff to say, if we look at something, can we tell whether it's this situation or this situation? And if it's this situation, then I may be able to start to get a sense of the 3D structure. And so what I do is I make movies. And I say, I know how far it is to each piece of the radio source. And so then I can basically put the radio source in a cube. If I know each piece is at a certain distance, some things have been rotated more, some things have been rotated less. So I just put them in the cube where they belong, where I think they belong, And then I just view the cube from different angles and see whether it looks coherent or whether it looks random. And the answer is, if you do some experiments, you can actually tell the difference by eye. This is where we need the mathematical tools developed, but for right now, we're just doing it visually. And so this is the lobe of a radio galaxy where I've just rotated it around, and there are these beautiful kind of long filamentary structures that show up, and I'm going to show you a couple of other examples of that. So this is that radio galaxy, a piece of a radio galaxy that we're looking at. This is the view face on, kind of looks like just kind of a tangled mess. And that was the movie of what it looks like when you assume that we can figure out how far each piece is from us. So let me see what else I have for a movie here. This is just the same thing. We're looking down from the top and from the side. And yeah, this is the same thing again. So this to me looks like a bunch of spaghetti noodles. And that's the kind of thing that people that are making models of how these radio galaxies work are going to have to try to figure out, how do we make a bunch of filamentary structures? And it turns out that it's not that hard, but hopefully we're going to be able to figure out which mechanisms are actually most important. We have to figure out whether these things are on the surface. We have to figure out whether they're through the body of the thing. And that's the kind of thing that we're trying to work on now. So let me skip there and just there's another one of these movies. So this complicated movie is just, it's this little thing that we're looking at, this double source here, and some of the other fuzzy stuff here is just the inner part of a nice radio galaxy. So here's the whole radio galaxy. Here's this little interior piece, this little inside piece, and here's a blow up of that inside piece. And when I play this game and say, I know which things are further away and which things are closer, then I can make the movie, and I can actually figure out which thing is moving away from me, which thing is moving towards me, what that structure looks like. So we found all different kinds of applications for this. We're figuring out internal structure in these jets that I was talking about, the magnetic field structure. And this is another picture. This was the one that I had on the cover there. This is the famous jet from M87, Virgo A, in the Virgo cluster of galaxies. It's been studied for many, many years in lots of different ways. And this is the first time there's been a 3D picture. And I'm saying it as if we've solved it. We haven't. There's lots of different things that can go wrong with this interpretation that you have to sort of take into account and check out. But I think there's a good chance that we are actually looking at the 3D structure here of this part of the jet, and just kind of rotating around and looking at it from different views. So I think that's it. Yeah. So that's the new tools we're developing. We're going to have so much polarization information coming out of Meerkat and ASCAP and the SKA that with tools like this, we're going to be able to hopefully get these 3D structures that we've been hoping for a long time. So that's it. Sorry for just sort of blasting on, but I'm happy to take questions.
I don't think anybody had any issues. I don't see anybody who just like, oh, I'm out kind of thing, and just like whatever.
We didn't lose the audience.
No. I've seen that some people had some connection issues. They logged off and then came back on, but I don't think anybody ran away. So.
Okay, so hit me with questions. You got a couple things in the chat. Do you want to read something
Yes.
to me?
There's a question here in the chat. Thank you, Dr. Rudnick. Excellent presentation, informative and entertaining. Brand new to this group, invited by a friend. Hold on, I might, okay. To check it out. Based on this presentation, I'll definitely be coming back for more. Well, thanks for joining, and I'm happy to have you. I have to ask you, I mean, are you planning on becoming a member? I know Professor Spengler can go on and on about that. And Professor Spengler, you don't have to raise your hand. You can just unmute, turn on your camera and start talking.
Well, I was trying to be for once being well behaved. So,
So Dan
Larry,
responded with a yes. And
yeah, that's it.
here's what I'm going to tell you, Dan. Our next member night is going to be February 3rd. And I try as much as I can to actually make pizza that day. I'm going to try to make it down to Iowa to make pizza that night too. So usually starts at 7:30 kind of thing. So hopefully see you there.
Well, good. Noah, your pizza advertisement is far more important than anything I have to say.
Well, I'm trying to get more members.
I do have a good question for Professor Rudnick here. I was intrigued with your noble effort to get the three-dimensional structures out of these. The question I have, you've talked to people in medical imaging because there's a huge amount of effort obviously has gone into just this with things like the radon transform and things like that. And I don't know much about it, but I know that there are, theorems and so on. There are a lot of mathematical results, developed for that. And I also know these tomography techniques have been applied to the solar corona. Now, the advantage the solar corona has, which is like the medical case, and unlike your case, it's kind enough to rotate itself. So you can
Right.
get a number of different angles, and you don't have that. But I was
Right.
just wondering if you, as they say nowadays, reached out to these other groups of people.
Yeah, very little. I've done a little bit. I think that the mapping of the Faraday rotation into 3D has enough challenges that I want to get that stuff sorted out first, because of course we can have the field angle or the density change as well as the path length. And so we've got to sort out those physical parameters a little bit. But once we do, then what the medical imaging people have is much more sophisticated visualization tools than typically we use in radio astronomy. So that's definitely something I would like to find somebody who's not retired to pick up on this. And so I'm twisting the arms of some people, because I think the visualization stuff is really where they have, a great deal to tell us. I'm not sure. I wouldn't want to jump into other types of transforms yet, because we know the Fourier transform is the mapping between the Faraday spectrum and the observations in wavelength space. Yeah, there's other things I'd want to explore first, but definitely on the visualization side, they have a great deal to offer us.
Any other questions?
Do you have something else in the chat? I see just.
I don't see anything else in the chat. What I'm
Okay.
going to do is I'm going to turn off the recording.
Okay.